We are starting our final chapter of graph theory today. We've got 3 lessons left in the school year, counting today. Today we're going to discuss trees, which are a new approach, not really new, a new approach for us to graph theory. So again, up on the screen here is a graph that contains seven vertices. It is not a complete graph. There are edges that are not there, but the edges represent roads between towns in a rainforest. And our job is to find the minimum cost to connect all of these towns to each other, the caveat being that we have to go along the roads because we can't connect 2 towns through the rainforest. They wouldn't stay connected. Something would sever that connection. So we have to build our network along the roads. Okay? Your goal here, that I asked you to do, was to find the lowest cost, the minimum network that would connect all of these towns. Okay? And that network would be that. That would be the best network that we could build that would connect all of the towns. Okay? Now, notice that this is different from Hamiltonian or Euler graph theory in that that connection, that grouping of edges that I've selected is not a circuit. It is not a path. In fact, that graph contains absolutely no circuits and is connected. This graph is what we call a tree, which is a new term for us that we'll define in a minute. Now, it's still, just like circuits and paths have and all the other stuff we've done, it does still have a weight. We could still add up all of those side lengths and get a weight. Okay, so this particular network would cost us $299. Now that's probably distance of some sort between these towns. That is the minimum network between these points. Now I say network because it doesn't necessarily fit what we've discussed already with Euler graph theory and Hamilton graph theory. It's another type of graph theory, networking graph theory. So this is our third graph theory unit because it's different from Hamiltonian and Euler graph theory. Today we are going to be discussing trees. Okay? We'll talk about how I did that in a later lesson because I used an algorithm to come up with that minimum network, and that will be discussed in one of our other 2 lessons before the end of the unit. So, a tree. A tree is a graph, and really we should say a connected graph that does not contain any circuits. Okay, it's a connected graph that does not contain any circuits. Okay, so on the left you'll see 4 examples there of graphs that would be considered trees. On the right, these are the ones I want to talk about. These are graphs that are not trees, and I want to talk about why they are not trees. Okay, graph number 1 is not a tree because it contains a circuit. That makes it not a tree. Okay, graph 2 is not a tree because it is not connected. It has 2 separate components. Those are really the only two things that can come up that keep a graph from being a tree. It's a tree if it's connected and does not have any circuits. So if it has a circuit, it's not a tree. If it's not connected, it's not a tree. Okay, it's that simple. So if we look at these other ones, okay, graph 3 again is not a tree because it contains a circuit. Ooh, wow, that got away from me quickly. And graph 4, just like graph 2, is not a tree because it is two separate pieces, two components. So once again, a tree is a graph that is connected and does not contain any circuits. So the first thing you're going to have to do on your assignment this evening is I've got, I think, a total of 8 graphs, and I ask you, is it a tree? And they're multiple choice. It's yes, no, it has a circuit, no, it's not connected, or no, it's not connected and has a circuit. Okay, so they're multiple choice questions. Some of these graphs, number 1 in particular does contain a path on the left. Okay, this graph does contain a path. That's fine, that can happen. That's not a problem in a tree. What it can't have is it cannot have a circuit. Okay, circuits are a problem. That would keep it from being a tree. Okay. It doesn't matter if it could be a path, it cannot have a circuit in it. So if it has a circuit in it, it is not a tree. All right. Grab your screenshot if you want one. We're going to go on to the next screen. All right. So the next thing I want to talk about is spanning trees. Okay. Every connected graph contains trees. Okay, they are subgraphs of the graph. So this graph that's shown on the screen here, it is not a tree. It has two different circuits in it. However, there are trees that exist inside of this graph that are subgraphs of this graph, like subsets. For instance, if I remove edge AD, oops, my pen tool, please. And edge GH. I know it's taken me a minute to draw this, but this is a subgraph. That is a subgraph of the original graph, okay? And that subgraph is a tree. It is a tree that spans the entire graph, okay? It connects all of the vertices in the graph, but does not contain any circuits. So this is one example of a spanning tree. And we could create other examples relatively easily by removing different edges from the circuits. Like for instance, if instead of removing AD, we removed AB. And we still remove GH, that is a different spanning tree, a different subgraph that is connected and is a tree. Okay? And just as easily, we could remove a different edge from the other circuit. Okay, so we could go back and we could remove AD again. But remove FH instead of GH. Well, that's still a spanning tree. It is in fact a different spanning tree a different subgraph of the same graph. All three of these are subgraphs of the original graph, and they are all three spanning trees. In fact, this graph has a total of 15 spanning trees. So here's where that comes from, okay? This graph contains two circuits. One of those circuits is length 5. That's this circuit here. Is length 5. And one of those circuits is length 3. So this graph contains 15 spanning trees because one circuit has 5 edges and the other circuit has 3 edges. So we just simply multiply the length of those two circuits, and that is where we get the 15 possible spanning trees from. Okay? So we locate the circuits, we count up their lengths, and then we multiply those lengths together, and that gives us how many spanning trees exist within a given graph. Okay? So I've drawn 3 of those spanning trees on the right there. I could draw 12 other different spanning trees because there are a total of 15. Okay, any questions before we move on into the examples? No one's jumping at the opportunity. Grab your screenshot now if you want it. Okay. So before we jump into the examples, I want to talk real quickly about what are the properties of a tree. So a graph is a tree if and only if there is exactly one path that connects any 2 vertices. If you can pick 2 vertices in the graph and connect them in more than one way, it's not a tree, okay? Because that means there's a circuit in there somewhere. A graph is a tree if and only if every edge in the entire graph is a bridge. Okay, again, it should be a connected graph with no circuits. What that means is if you remove any edge, it's no longer connected, which means every single edge in the entire graph must be a bridge, which we discussed way back in graph theory terminology, back at the beginning of all this e-learning fun. Okay? If a tree has n vertices, it must have n minus 1 edges. So if it has 10 vertices, it has 9 edges. If it has 12 vertices, it will have 11 edges. There will always be, in any tree, one less edge than there are vertices. So if there's 32 vertices, there's 31 edges. 8 vertices, 7 edges. Okay? Similarly, a connected graph that has n vertices and n minus 1 edges has to be a tree. There's no other way to have that happen. Okay? A connected graph with n vertices and n minus 1 edges must be a tree. Grab your screenshot if you want one. We're going to be moving on into the examples next. This is leading up to what I consider to be one of the easiest graph theory assignments of the entire quarter of graph theory that we do. Okay, it's easier than any of the ones we did last unit by far. Okay, should be a relatively easy weekend for us. All right. So we're going to go back to that spanning tree skill, and we're going to determine the number of possible spanning trees in each of these graphs. Okay, starting with graph number 1. Graph number 1 contains 2 circuits. One circuit is length 3, one circuit is length 4. That's 1, 2, 3. 1, 2, 3, 4. Okay? So the number of spanning trees would be 3 times 4, or 12. There are 12 spanning trees in this graph. Okay? The next one's a little bit tricky. Okay, but not really. By throwing that shape inside the other shape, I'm trying to confuse you. But in reality, it wouldn't matter if I drew it in there or if I moved the whole triangle up above and kept it connected, it would be a separate circuit. So that graph contains 3 circuits. It has a triangular circuit, which would be length 3. It has a pentagonal circuit, that's length 5. And it has this diamond shaped, which is length 4. Now, whether it has 3 circuits, 12 circuits, 28 circuits, that doesn't matter. What matters is you multiply the lengths of the circuits. So this problem would be 3 times 4 times 5, or 60 possible circuits, possible spanning trees. Okay? Try that last one, please, while I add a little bit more to this for our completed notes that I post later. The length of the circuits, yes. You count the length of the circuits and then multiply those numbers together. Okay, that last graph contains 2 circuits. We have this circuit that is in the shape of a star, 4, 5, 6, 7, 8, 9, 10 edges. Yep, 1, 2, 3, 4, 5, 6 in the other circuit. So 10 times 6 is 60 possible spanning trees. Okay? Relatively simple idea. I've got a couple of those on the homework as well. Count up the length of the circuits and multiply. Okay? Take your screenshot if you want one. We're going to be going to the next screen, which I think is the last screen of the notes. I'll check before we start it. Nobody's throwing any questions in there, so I assume we're good to go. Oh, that was the last one. Okay, couple things real quickly before we continue. A couple things to keep in mind that will come in handy on the homework. Number 1, is that all graphs, all they really require to be considered a graph is a vertex. 1 vertex. Doesn't need an edge. Doesn't need edges to be a graph. All it needs is vertices. Okay? Okay? Any graph, okay, there's your properties of trees again. Any graph that has n vertices and n minus 1 edges is a tree. So if it has 1 vertex and 0 edges, that's a tree. So keep that in mind. Okay? Yes, at the end here, I will scroll back up and give you guys the opportunity that missed out on the screenshot opportunities. Okay. Okay, that is, it does, in fact, does not need to have edges. Number 2, If a connected graph, and it should say connected graph, doesn't contain any circuits, it still has one spanning tree. The entire graph is a spanning tree. It is its own spanning tree, you might say. Okay, so something to keep in mind. Okay, I've got a Google Form assignment for you. I'll be posting that to Google Classroom shortly.